Okay, so in this video we're going to take a look at systematic reviews and meta-analyses. So just to jump into the definitions, well, a systematic review is basically you gathering a whole bunch of different evidence, a whole bunch of different studies that have asked similar research questions and basically just coming up with a certain type of evidence, a certain type of conclusion. And a systematic review doesn't necessarily have to include a meta-analysis, but if it does, then a meta-analysis is something that essentially pools the results of all of the independent studies that have asked a similar question together and comes up with an overall pooled result of the treatment effect. Now the idea is that we always want to have a body of data that has been systematically reviewed, right? But we don't want to pool results all the time. We don't want to statistically average the results together, because sometimes the results are not fit for meta-analysis. And we're going to talk about why they might not be fit for meta-analysis at some points. So basically the steps to performing a systematic review, and we're going to go through, there are 8 steps, we're going to go through all 8 steps, is the first thing, I'm just going to go through them one by one. The first step is to essentially formulate the research question. So ask the research question, right? And you want to make sure that the research question is formulated a priori. You've asked the research question a priori. This goes back to why asking the research question post hoc is just something that's very easy to do. Obviously, if you see the results and then you ask the research question, well, you can just make something up based on the results that you see. So the research question must have been asked a priori. Okay, and the type of research question depends on the type of studies that you're including in your systematic review. So if your systematic review includes, if your systematic review is a therapy type of question, then the PICO components, for example, are going to reflect the PICO components for a therapy study, and so on and so forth. So that's the first step. It's always asking that research question, and you want to make sure that it's done a priori. The second step is to describe the sources of potential heterogeneity. So you want to say a priori, any sources of heterogeneity. And heterogeneity is essentially just a term that tells us why different studies that are asking the same questions are coming up with different results, right? And there are 2 different sources of heterogeneity. So we have clinical heterogeneity, and clinical heterogeneity refers to external validity. So it refers to the differences in the applicability of results. And then we have methodological heterogeneity. So this is basically heterogeneity that's as a result of internal validity, right? The methodological ways that the different trials that we've included in our systematic reviews are differing. Perhaps they've randomized differently. Perhaps there's allocation concealment present in one and not in another. Perhaps there's different follow-up rates in one, and there's missing data not at random in one and missing data completely at random in another, right? So that's what I mean by heterogeneity, and you need to make sure that you define your sources, or you define your hypotheses for heterogeneity at the very beginning, so that when you go back to look at it, when you've done your meta-analysis and you see that there is heterogeneity, that you can say, okay, I'm going to test this hypothesis for heterogeneity and see if it does anything to reduce the heterogeneity. Okay, so you want to make sure that you've identified and described the sources of heterogeneity. And when you do, you also want to make sure that you say, that you indicate the direction of the heterogeneity. For example, you might want to say that studies that have people who are blinded show smaller treatment effects, right? That's showing direction. But sometimes what people will say is that studies who have people blinded, they're going to be different from studies that weren't blinded. It's better to say that studies who had people blinded will show smaller treatment effects in favor of the treatment or the experiment compared to the studies that didn't blind the outcome assessor. So it's a lot stronger when we indicate that directionality. Remember, we said smaller, right? And that is the term that's indicating our directionality. The third thing we want to do after asking a research question a priori, after defining a list of potential heterogeneity sources, the third thing we want to do is actually conduct the literature search. We want to make sure that our literature search is exhaustive. So conduct literature search. Okay, and the manner in which we have to do this is, first we can definitely look at peer-reviewed sources, right? So we want to make sure we're looking at trusted databases like, for example, Medline, PubMed, Embase. You know, we want to go through a whole bunch of different electronic databases in peer-reviewed articles and so on and so forth, right? But you also want to make sure that you're not neglecting any sort of unpublished or non-peer-reviewed articles, right? So you want to make sure that you're looking at the gray literature, like theses, conference proceedings. A lot of the times that things that are going through conferences, some of those abstracts in the conferences never actually get published, right? So you want to make sure that you're including gray literature also, and literature that might not be peer-reviewed or published into your literature search. So you want to make sure that you're also using good databases also. Okay. Now this brings us to the idea of, how do I know that my search was exhaustive, right? I've conducted a literature search, but how do I know that if it was exhaustive? And there's a type of bias that can be introduced in your conduct of literature searches, and that type of bias is known as publication bias. Okay, publication bias. And essentially what publication bias is it's basically the omission or the removal potentially, or just the ignoring of studies that have shown, usually studies that have shown small negative results, right? So usually what we're doing is we're not including small negative studies because they're just not favoring our hypothesis. And publication bias is also a lot of times present because positive trials are more likely to a whole bunch of different types of biases. For example, positive trials are more likely to be cited by others, so there's some sort of citation bias there. They're more likely to be published in English, so there's language bias there. They're more likely to be published rapidly, so there's time lag bias. They're also more likely to be published more than once. That's called duplication bias. And they're also more likely to be published than those negative trials. So that's publication bias, right? And when we start to exclude those small negative studies in our when we're conducting our literature search, we're starting to overestimate the treatment effect, right? Another thing we want to do is look at who funded the study when we're doing a critical appraisal of some sort of systematic review. Obviously, if it was from someone who benefited from publishing the positive results, then it may be susceptible to publication bias because of the fact that there was some sort of interest in that sort of publication going on there, right? So you want to make sure that you look at a whole bunch of different things when we're conduct of the literature search that is happening over there. Because obviously leaving out small negative studies is going to overestimate our treatment effect. Now, how do we actually go ahead and detect that publication bias? So we're still in the third step. We've conducted our this is falling under the third step in the conduct of literature search. So how do I go about detecting publication bias? So there's a method. It's called the funnel plot, and it's essentially a graphical method that helps us detect publication bias. So I'm going to erase this, and you're just going to need to remember that we're on the third step, and we're going to talk about the funnel plot. Okay, the funnel plot, again, is a graphical method that's going to help us detect publication bias. Okay, and the problem, actually, let's just look at the funnel plot first. So we have this on our funnel plot, and on the bottom we have effect size reported. And over here, on this y-axis, we're going to have standard error reported. Okay, and essentially, let's just draw a line here. And this was, of course, the important difference line up. And then I'm just going to draw a little bit of a funnel. And you'll see that everything is converging towards the top, right? What these black dots represent are positive studies, and these open circles are representing our small negative studies. Okay, this is what a funnel plot looks like. It's supposed to look pyramidal. I might have added a couple of extra dots that makes it look less like a pyramid, but essentially a funnel plot looks like a pyramid, right? And you can see that as we go down, right, when we go down, because we're taking the actual standard error of the log, right? We're taking a logarithm. So as we go down, our standard error is increasing, and you can see that it makes sense because our smaller studies are actually dispersed here at the bottom, right? Whereas our larger studies get dispersed here at the top. And it makes sense because our standard error is smaller in our larger studies, and our standard errors are always bigger in our smaller studies because they're more prone to random sampling error. You can also see that our effect sizes, this could potentially be an odds ratio, for example. You can see that our effect sizes are also varying very widely in the smaller studies. Again, could be potentially due to random sampling error. In the larger studies, they're a lot more closer towards this line right here. So the idea is that if I've not included small negative studies, right, and potentially I have a funnel plot that looks something like this, right? Well, first of all, it doesn't even look pyramidal to me, right? It doesn't look like a pyramid to me. The whole bottom right corner of that funnel plot is missing, right? So I don't have any small negative studies going on here. So I can look at that funnel plot and say, okay, there's probably some sort of publication bias going on, right? But the problem with funnel plots is that it's heavily reliant on larger studies to guide its assessment of whether or not that publication bias exists. So consider if the large study is biased, right? Then we're just basically trying to correct a bias. Then we're trying to look for something that is biased with something that is already biased. So that's very hard to do, right? And then we want to take a look at what if we had just very few amount of studies on this funnel plot, right? What if we didn't have as many as it's plotted here, right? So it's obviously very difficult to tell if we only had 4 studies here whether or not publication bias also exists. So funnel plots are also very prone to bias. So if we are susceptible to, or if we do have any sort of publication bias happening, how do I go about correcting for publication bias? And there's a common statistical method used, and it's called the trim and fill method. The trim and fill method. And the trim and fill method is a statistical method that is going to correct for publication bias. And again, the similar idea applies here, that it's very reliant on larger studies. So if the larger studies are biased, then we're trying to correct a bias with a bias. And it also could be potentially prone to power, right? So if we have a very low amount of studies, then removing studies using trim and fill might not be a good idea. So the general idea behind trim and fill is that it's going to go through your whole systematic review, and it's going to look for evidence that there are some small negative studies perhaps missing. And what it does is that when it finds evidence that perhaps small negative studies are missing, it's going to remove the small negative small positive trials, the counterparts to the small negative that are missing, to arrive at a more balanced estimate of the effect. And that's the general idea of the trim and fill method. All right. So that brings us to the 4th step in conducting a systematic review. So we've now talked about conducting literature search and how we know whether or not that literature search was actually exhaustive. The 4th step that we want to take is, let me just get the marker moving here. The 4th step we want to take is to define the eligibility criteria of our studies. Define eligibility. And we want to make sure that we select relevant studies. So we want to make sure that selecting relevant studies. All right, and the way that we do this is we go through a screening phase. All right, and there are 2 steps in this screening phase. In the first screening phase, we get basically reviewers, pairs of reviewers. right? And the first thing that they're going to do, or first thing we're going to do, is define eligibility criteria of the articles we want included in our systematic review. And what we're going to do is we're going to create some sort of some sort of reviewer data form, so that the people who are doing the review of the articles to be included in the systematic review and to not be included know what they're looking for, right? And then what they're going to do is they're going to go and independently review the titles and abstracts first, just the titles and abstracts, and they're going to classify them either as exclude, or they're going to classify them as review in full text. Okay? And what we do after they've done that is we're going to try to determine and report the agreement. And we're going to report an agreement statistics between the two. And we have to report an unweighted kappa, right? This is the dichotomous measure. They're going to either report it as a exclude, or they're going to report it as a review in full text. So we're going to report an unweighted kappa. And if our unweighted kappa is not very high, in other words, if it's like at, let's say, 0.2, well, that's not a very high agreement statistic, right? Kappa ranges from 0 to 1. So we need to make sure that when it ranges from 0 to 1, that it's close to 1. Okay? And once we've done this, and we've determined perhaps that there is a good agreement statistic, then we can go ahead and retrieve all the articles that is review in full text. We're going to go jump into this now. And we could also potentially include those that they didn't agree on. So perhaps one said exclude and one said review in full text. Well, we'll include that one too. And perhaps, yeah, we'll include that one too. So we'll include and jump into the next phase of the screening. And that phase is the full text review. So now, this was phase 1. Now we're going to get into phase 2. So now we're going to basically go into review in full text. And we're going to classify in here either exclude, include, or uncertain. Same thing's going to happen. We're going to have a reviewer data form. We're going to define the eligibility criteria. They're going to go ahead, the reviewer is going to go ahead and report them as this, right? And we're going to report an agreement statistic, an unweighted kappa, and for the ones that we disagreed on, so perhaps these and these, and for the ones that we were uncertain on, we're going to get a third party. And we're going to try to get a consensus on the disagreement, and we're going to get a third party, and they're going to make the decision on whether or not we're going to include them in the fold. We're going to include them once we've reviewed them in full text. For the studies that we've excluded, we want to make sure that we keep a record of the ones that are excluded and provide reasons as to why they were excluded. We need to make sure that an article that did exclude studies tells us why they've excluded the studies, right? Again, perhaps they could have been publication bias, so we need to make sure we know why they've been excluded. So yeah, that's step 4. Let me just erase this so we can get on to step 5 now. The 5th step is assessing the quality of the included studies. This is not going to be a huge topic. But when we go ahead and assess the quality of the included studies, we want to make sure that the quality of the studies that we're including is great, right? We want to make sure that they have good internal validity and good external validity. Remember that the pooled estimate, the meta-analysis that we perform, if it's reasonable to perform a meta-analysis, is only going to be as valid, right? The pooled estimate is only going to be as valid as the estimates that were provided by the studies. So if the studies were not good, then our pooled estimate is not going to be good either. So what we want to do is conduct a quality assessment scale. And we want to make sure that we're using the appropriate quality assessment scales, right? For example, when we do RCTs or when we're performing an RCT, you want to make sure one of the best tools to perform a quality rating scale on an RCT is the Cochrane Risk of Bias tool. So look at whether or not, first look at the study design, and then look at whether or not they've used an appropriate quality of rating scale, right? Another thing to essentially assess whether or not they've used an appropriate quality of rating scale is to determine whether or not that quality of rating scale is actually asking about any sort of internal validity issues. Sometimes what quality of rating scales do is they actually don't ask about internal validity, and they report that and they ask about external validity questions, right? So the questions are not, quality of rating scales should be dealing with internal validity first of all. If the quality of rating scale is starting to deal with questions of external validity, or if they're dealing with reporting issues, for example, they're just asking whether or not something was described in the manuscript, well then this is not a very good scale in determining the quality of the included studies. So we want to make sure that we're using appropriate quality of rating scales and that the quality of rating scales are really trying to discern whether or not there's good internal validity in the studies that we've included. Now, the next thing we want to do is extract the data, right? Or actually, let's stay on here for a little bit, quality of rating. Again, quality of rating, the same thing is going on when we do the quality of rating. We want to create pilot forms or reviewer data forms so people know what they're looking for. We want to have some sort of consensus at the end of the day, report an agreement. Now, if the quality of rating score or scale was some sort of continuous measurement, right? So if the quality rating is some sort of score, then we're going to report the agreement statistic as an ICC. If the quality rating is some sort of ordered category, then we're going to report it as a weighted kappa. If the quality rating was a non-ordered category, then we're just going to report it as an unweighted kappa. Okay? The next step, so after we've gone through quality rating, the next step is to essentially jump into extracting the data. I'm not going to write this down because really extracting the data is going to be similar steps. We're going to create a reviewer form. We're going to try to reach a consensus and so on and so forth. And then we're going to extract the data and report certain, report the data. We're going to extract the data and then we're going to report it and report it down somewhere. But the seventh step, because extracting the data was the sixth step, the seventh step is really the important step. And this is the step where we want to conduct the meta-analysis. First of all, is it even appropriate that we conduct the meta-analysis? Right? And the way that we tell is, first of all, we go ahead and conduct the meta-analysis, right? But before we conduct the meta-analysis, we want to make sure of two things. Okay? The first thing that we want to make sure is whether or not we're using a standardized mean difference, or let me write this, what step we're on. So we're on the meta-analysis step. Now we performed our systematic review, extracted the data, and now we want to see whether or not it's appropriate to do a meta-analysis. Well, the first thing we want to consider is do I report standardized mean differences or do I report weighted mean differences? And really this is only going to be of importance when we're at continuous outcomes, when our outcome is continuous, right? So weighted mean differences are used when every single included study has used the same outcome measure for whatever it is you're looking for. So let's say your outcome measure or your outcome is pain. If they've all used the pain NRS scale, for example, then you can use a weighted mean difference, and you can just average the score together and find a score. But if the pain was measured by using different outcome measures across the included studies, then we're going to have to use a standard mean difference, right? You can't just get a valid answer by averaging all the scores together because they're obviously being measured on different metrics. So what you're going to do is you're going to first standardize them all on a normal distribution. And then you're going to see how many standard deviations each of them are away from the mean of 0, right? And that's when we use a standardized mean difference. The second thing you want to consider is whether or not you actually, whether or not you want to use a fixed approached model or a random approached model. Or random approach. And I'm not going to get into discussing when we want to use fixed or random effects model. Just know that these are two different things that we need to determine. And there's going to be a huge, I'm going to basically include an explanation in the description of the video about fixed or random effects and when we should use fixed and when we should use random and what it means for a study when they use random effects and what it means for a study when they use fixed effects models. But this is the second consideration you need to make when you're conducting a meta-analysis, or before conducting a meta-analysis rather. Okay, so just read the description to come up to figure out basically something, to figure out what it is for fixed or random effects and what the difference between that is and why we need to figure out why we need to use one over the other. Alrighty, so now we're ready to conduct our meta-analysis. Okay, so let's say we've conducted the meta-analysis and we've pooled the study together. We've pooled all of the studies together and we've come up with a result. But the results are so different from one another, right? So there is heterogeneity, right? Each of the included studies are coming up with different answers for some reason, right? Well, at this point we could say meta-analysis is not appropriate unless we can use our a priori hypotheses for heterogeneity to explain the heterogeneity. So what we want to do is, let's say we want to basically separate our groups into subsamples now. Let's say our heterogeneity, and we hypothesize that our heterogeneity was because some studies were blinded and some studies were not blinded. Well, we're going to separate these studies based on blinded and non-blinded. Separate the studies based on blinded and non-blinded. And if at this point I can get rid of the heterogeneity, I can show that these studies, the results are now more consistent between blinded and non-blinded, then I'm going to report the results of the pooled blinded results, and I'm going to report the pooled non-blinded results. But if again I can't explain my heterogeneity, then I'm going to reverse this and I'm going to go look for my next a priori hypothesis. And if at the end none of my a priori hypothesis can explain my heterogeneity, then I'm not going to pool the results, and I'm going to say at the end of my systematic review that there was no way that I could pool the results because heterogeneity could not be explained. But obviously, if you could explain your heterogeneity by perhaps splitting into more subsamples based on your a priori hypotheses, then you can pool them individually. Okay. Now, how do I know when there is heterogeneity? Right? What are the different types of things that I can use to assess heterogeneity in systematic reviews? The first thing is a forest plot. So a forest plot is going to look something like this. Okay. And let's say on this side I'm favoring treatment, and let's say on this side I'm favoring control, and I'm reporting it as risk ratios or odd ratios or whatever. And I have my point estimates. My confidence intervals are going like this. Or actually, let me draw different scenarios for you guys. So let's say that I have confidence intervals that look like this. And then I have a diamond shape like this. That should be a diamond, by the way. Okay. And then this is my point estimate. So these are all point estimates. A couple of things that I can do to assess whether or not heterogeneity exists. The first thing I have to do is understand what my forest plot is. My forest plot, usually what it does on the sides here is it gives me the different studies. It gives me the different types of events that have occurred, and these in the treatment group and in the control group, and it gives me the weighting of the studies, right? And the weights of the studies are distributed so that the larger studies get more weight because they're less prone to random sampling error, and the smaller studies get less weight because they're more prone to random sampling error. And then they start to report their results, like the risk ratios and everything for each study. So the risk ratio for this study would be reported in the point estimate, and the confidence intervals around that risk ratio, point estimate, etc., etc. And then here is my pooled result. It should look like a diamond, right? So this is going to be what I'm interested in. This is my pooled result, and it's going to give me essentially a risk ratio confidence interval, which is going to be the width of my diamond, and it's going to give me a point estimate, right? So how can I assess heterogeneity here? Well, this shows me that there's really no significant heterogeneity. Everything is on one side of the no difference line. The confidence intervals seem to overlap pretty fairly. The point estimates seem to be pretty consistent. And the diamond shape is all in all not touching the no difference line. So there's no heterogeneity over here. But I'm going to give you an example of something that does look like it has heterogeneity, right? Let me erase this. And let's say that confidence interval here, a confidence interval here, confidence interval here, confidence interval here, and let's say that my point estimate for my diamond has touched, and this is my point estimate, right? So this study looks to me like there might be some sort of heterogeneity, right? This study is crossing that no difference line, so I'm unsure. This study is way on the side of favoring treatment. This study is way on the side of favoring control. Point estimates, confidence intervals are not really overlapping. My point estimates are widely variant, right? And my overall pooled estimate is touching that no difference line, right? So now I'm uncertain whether or not there is a difference. So that might show me that there is heterogeneity. So what I should go back and do is now pull my results based on my hypotheses for heterogeneity to see if I can get my confidence intervals overlapping, to see if I can get more consistent point estimates, and to see if I can get my diamonds, my pooled estimates, to be on one side of that no difference line instead of touching that no difference line. I don't want this to happen, right? Otherwise I'm unsure of the differences. Okay. So that's how you can assess visually for heterogeneity. But you can also statistically assess for heterogeneity. And we're going to take a look at a couple of statistics for heterogeneity. One thing you might want to know is that depending on my outcome, I favor the treatment on one side and I could favor the treatment on the other side. So if my outcome is beneficial, for example, or let's say my outcome is harmful, right? So I'm looking for mortality rates, right? Well, how do I tell which side is favoring treatment and which side is favoring control? So if the outcome of an event is bad, like adverse, so it's mortality, for example, the results on this side of the line, on the left side of the no difference line, or the vertical line here, favor the intervention over the control. And that's because the estimates over here, it means that there's less than one risk. It means that the risk is smaller in the people who got the treatment compared to the people who got the control. But if the outcome is desirable, if the outcome is some sort of beneficial, like survival, for example, and then the results to the right of this line are going to favor the treatment, and the results to the left of this line are going to favor the control, because on this side we're going to say that people who have the treatment, right, if the outcome is beneficial, then this side favors the treatment. People who have the treatment are more likely to have this outcome, which is survival, over the people who didn't have the treatment. So you have to make sure that you know what outcome it is that you're looking at. Okay, so now to assess the statistics for heterogeneity. So I've just talked about when it is appropriate to have a meta-analysis and when it's not appropriate to have a meta-analysis. Let's say that we're still not sure. We've looked at our forest plot and we're unsure of whether or not it's possible to perform a meta-analysis, right? Then I can start looking at my statistics. Statistics are something I do want to look at anyways. So we have two statistics that we'd like to look at. The first statistic is called Cochrane's chi-squared value. And the second statistic is I-squared. This is also called Cochrane's Q. And essentially, this is going to test, this Cochrane's chi-squared is going to test whether the estimates of the effects of the study are similar, right? And a p-value that is less than 0.05 implies that there is a difference between the groups. So this means that there is heterogeneity. Heterogeneity. Okay, so p-value on your Cochrane's chi-squared or your Cochrane's Q of less than 0.05 implies that there's heterogeneity. But the problem with the chi-squared is that it's actually hugely affected by the number of studies that you have in your review. So if you have a small number of studies in your review, right, that chi-squared test might not indicate significant heterogeneity, but there could have actually been heterogeneity. You just weren't powered to detect that significance, right? If you, on the other hand, you had a lot of studies, you were somehow overpowered, that chi-squared could have reached statistical significance. It could have detected significant heterogeneity or some sort of significant result, even if the studies were not that importantly different. So that brings us to I-squared, where I-squared is it's basically the estimate of the percentage of total variation that is a result of heterogeneity among studies rather than chance. So I-squared values range from 0 to 100, and a low I-squared value is 25%. A moderate I-squared value is 50%, and a high I-squared value is 75%. Right, and I-squared values actually overcome that idea, overcome the disadvantage that chi-squareds have, because because I-squared is not affected by the number of studies that is included in your review. So you want to make sure that you look at I-squared value and I-squared values. So once you've determined I-squared and chi-squared, and you've looked at your forest plots, you want to make sure that you don't have any heterogeneity in order to continue with a meta-analysis. If you do have heterogeneity, then do not continue with your meta-analysis. Evaluate your sources of heterogeneity, which is the 8th step. And if you cannot evaluate, and if you've evaluated your sources of heterogeneity and nothing is explaining your heterogeneity, well then what you want to do is not pool the results and say that you weren't able to basically that you weren't able to explain your heterogeneity. If you were able to explain your heterogeneity with one of your hypotheses, your a priori hypotheses, then pool the results separately. Okay, and finally, the final thing we're going to take a look at is precision. How do we evaluate the precision of a systematic review? And this is essentially going to be using the optimal information size. Obviously, we can use the confidence intervals, and the confidence intervals are found in the forest plots, but we can also use the optimal information size. And this is actually usually given by grade, which is basically just a series of articles that have been given to help us assess systematic reviews and the quality of systematic reviews. So the optimal information size is basically the number of patients that you need in order to report an adequately powered trial, assuming that there is a modest treatment effect. So your OIS, which is essentially just a sample size calculation, is calculated based on the type of study that you have included. So for example, if you have a prognostic study systematic review, then you want to calculate your sample size based on the sample size calculation for a prognostic study. If it was an RCT, then you can use one of those equations for an RCT to calculate your optimal information size, and so on and so forth, right? So you want to make sure that you calculate your OIS, and you want to make sure that there was some sort of precision there. So how do we determine what was precise and what wasn't precise? So let's say that your OIS is not met, right? So then basically what you do is you would rate down for precision according to grade, right? If your OIS is not met, then you don't have adequate precision unless you have a very large sample size and that you have a lot of events happening. Otherwise, if your OIS is not met, then you don't have adequate precision. If your OIS is met, the next thing you want to take a look at is your confidence interval. If your confidence intervals exclude the no effect line, exclude the no difference line, then you can say, okay, I have good precision. If they don't exclude the no effect line, that is to say they cross that no difference line, right, especially for your pooled estimate, then you probably don't have adequate precision. Okay, so you want to take a look at not only just the OIS but also the confidence intervals. The confidence intervals are very important, and something that you might finally look at is calculating a fragility index. And a fragility index is basically just tell you how many events do I need to change my p-value that was statistically significant to a non-statistically significant p-value. So let's say I had a beneficial outcome, right? So let's say I was giving out an antibiotic, and this side I had my control group, right? And these people weren't receiving it. And I expected people were dying, right? Because they weren't receiving the some sort of treatment, and was basically trying to see whether or not people were improving, right? Well, if in my treatment group I start to see, well, let's say I have 9 people in my treatment group and 9 events in my antibiotic group, meaning that so 9 people died, but let's say 15 people improved, right? Let's say my control group that I had 15 people die and I only had 1 person improve, right? Well, and then let's say that I calculated a fragility index, and my fragility index was 7. Right? What this is saying is that in my antibiotic group, I need 7 more of these events. And so let's say before I actually calculated my fragility index, my p-value was less than 0.05. What this is saying is that, and my 7 is my fragility index, what this is saying is that I need 7 more people to have this event, to have this negative event in my treatment group in order to switch my p-value from a statistically significant p to a non-statistically significant p. And obviously, the lower your fragility index, the more fragile your p-value is, and the more fragile your results are, and the less precision you have around your estimates. So that is about it for systematic reviews. That's also about it for this entire series. So I hope that this series has helped you in one way or another. And yeah.